King to Dodge.
Yeah.
Tonight, we have Fred Erickson, KB0LF, who's been a member of our club here the last 6 months. And he's going to do a presentation on radiation patterns of wire antennas. This is an EZNEC computer program. Fred has experience doing something similar. He did modeled electromagnetic pulses on aircraft, satellites, and ground systems, and also lightning pulses. And he did shielding work for EMP at the Stratcom Command Center. So anyway, welcome, Fred.
Thank you. There are a couple of fairly inexpensive and fairly easy to use computer codes that do modeling. And it's something that I have an interest in, and I thought I would share with you some of the models that I've done, tell you a little bit about a couple of the models, and show you how one of these computer codes is EZNEC, how it works. It's pretty simple. I'm familiar with two codes. One is EZNEC. It's based on a numerical electromagnetic code NEC. There's a shell that provides the data inputs to NEC. It runs NEC, and it gets back the data from the computation. There's another code that NEC you buy. There's a version of it. The basic version of it is $89, I think. The version that I'm going to show you here is about $130. There is a free version you can get off their website, which is www.eznec.com. You can download it, and it's a full-featured version of the code, only it limits the number of wires and the number of segments you can have. There are other codes. There's one with the acronym MMANA. I have not used it. It's shareware, so it's free. It was originally designed, built, and distributed by two German hams. The current version of it has some upgrades, I think, from what originally came out. There's a Japanese ham that's a part of their group now. That code I haven't tried. One of the things that I like about EZNEC is a very stable code. The man that did this probably was involved with EZNEC 40 or 50 years ago. He probably built the shell 25 or 30 years ago. There's a lot of testing to it. There have been no issues with viruses or problems with EZNEC. The other code I don't know. In any event, one of the reasons that I wanted to give a talk also is to see if I could interest someone in trying this out. If you do any sort of work with wire antennas, this sort of modeling can be helpful in understanding how the antenna works and how changes in the configuration of your design impacts the pattern. So let's see here. So here are the two programs, EZNEC based on NEC. The MMANA code is based, this is actually MMANA-GAL, and I'm not too sure what all of that pertains to, but it's also a NEC-based code. NEC models thin wires. The code itself partitions the wires into little segments, and the code goes ahead and calculates the currents on the segments of wires from a source that's in your antenna. And then from the segment, the currents on each of the segments, you add that up at different angles, and that's how you get the radiation pattern. So let's see. I thought what I would do is start with an antenna type that everybody knows, and I'll show you the interface with EZNEC for this. This is a dipole, half-wave dipole. This is a pattern looking down. If you imagine that the wire for the dipole is horizontal, then the radiation pattern in the azimuth would be two loops. The modeling that I've done is similar to this, and in the patterns that you see that I'll show you, I have always chosen the direction to the right to be east for an azimuth pattern, and the direction up top to be north. So this is out of the handbook, and let me see if I can bring up EZNEC for this. New graphs. Here's EZNEC. I can't increase that any more than you see there. I don't know how. But this is 90% of the interface for this code. So this is the shell, and there'll be some inputs out of the shell, and one of the inputs I'll show you here in a second is the wires. This is the place where you need to specify the lengths and angles and positions of the wires that are part of your antenna. I'll show you that in a minute. There's a neat capability to show what you have modeled with your wires. It's one nice thing is it's a sanity check. After you've put some things in, if you've got a wrong number, it'll show you the one of the wires for the antenna to be off in left field. And this icon down here starts the program and runs. So I'm going to do a dipole. The wire file, there's 3 wires. The way that you put a source into your model is to have a short segment and specify some voltage on that segment. And so the dipole is essentially 2 segments, 2 long segments, and a short one in the middle for the source. Wire 2 is the short segment. This is in feet. You can do this in meters. I forget the other units, but it's really convenient. This is a half-wave dipole on 40 meters. So the segments are 33. Each side is 33 feet. There's a section in the center that's just a couple of feet. It goes from -1 to 1, and that section is the section that has the source in it. So this is a key part of the modeling. It's the hardest part. I won't go into a lot of detail if somebody wants to talk about that. The hardest thing is to figure out the size of your antenna and then figure out the XYZ coordinates. For this antenna, that's simple because it's straight. And here's the viewing capability, which is some of this is really neat. This is also up a quarter of a wave and 40 meters. So this is up 33 feet. One section is 33 feet. Another section, 33. The source is in the middle, and it's a couple of feet long. So next thing you do, run the code. Let's see. Let me click this out. Had it. What's going on here? That's the plot. I guess because I've run this already, you see the answer. It'll blink usually when you've made a change in this. It'll blink a little bit. It's a little bit hard to see here. This is a top view. This will be east, the X direction. This will be north. This is a donut. Okay. So in 3 dimensions, it's a donut, and this model is with no ground. So it's a wire in free space. You can put an ideal ground in, or you can put a real ground in, and I'll show you an example where a real ground made a huge difference in what the antenna pattern was, an antenna that I actually had. Cool thing you can do slices. Take an azimuth slice. In this case, we'll do it at 0 degrees, and you do a 2D plot. And there's get this down, there's the plot that was in the ARL handbook. So the ARL handbook, you had a donut for the 3-dimensional pattern, and you slice that in the azimuth, and you got 2 loops. There's a number of things that the code will do, but I think maybe what I'll do is another model here. Let me tell you a little bit about where I live. I live south in Murray. I don't know if you folks know where that is. If you head south past Plattsmouth, keep going on Highway 75 towards Nebraska City, maybe a third of the way, there's a little town, sort of farming community, 1 mile west off Highway 75. And this is a Google Maps view, satellite view. North is up, east is to the right, and there's a park that maybe you know about. This is the park, and our property. Jeannie and I live in a home that's here. This is our driveway. Our property is long and thin in an east-west direction. It's got a set of pine trees out in the back, big old sycamore back here. This is a park. If there used to be a very nice 4th of July fireworks display from here every year. Pretty active baseball leagues here, and a park up here, and there's a water tower here. You can see the shadow of the water tower there a little bit. Let's see. Do one more of these. I wanted to get on 80 meters with an omnidirectional antenna. So I marched out and started pacing off distances in this area where all the pine trees were. And when I did that, I realized that I could pretty easily get a loop that was about 500 feet long. I'd never been on 160 meters. I always wanted to be. 500 feet's about a wavelength. And so instead of putting up a loop for 80, I put a loop up for 160, which was cool. Never been on the band before. It's not really a loop, it's a pentagon. And it's a pentagon because that's where the trees were. There's a sycamore tree here. There's a little old tree out here in the corner. There was a big old pine tree here. There's a maple tree back here, and there's a pine tree where the arrow is. North is up. This is Mark Spangler's corn/bean field. This goes about a half a mile to a mile with almost nothing to the north. And when you get a north wind, it blows across there. And it hits our little stand of trees. So I put up a wire. THHN out of Menards, 500 feet. Back when I bought it, I think it was 80 bucks. Insulated. I didn't take the insulation off. I just strung it through the branches of the tree. I did it in December when there was snow on the ground, which was sort of stupid, but well, you know, that's when I realized all this was going to happen. I was excited. So like a dummy, I went out and put on my boots and strung it out there. But of course, that's December and January is a great time for 160. And it's fed in this corner. So, you know, one of the questions that I had was, so I fired it up and I used it for a year and it worked pretty well. And it was good for regional communication on 160. Mostly CW is what I did. You know, Minnesota was good, Colorado was good, Kansas or whatever, didn't go too far, but it was pretty uniform. It seemed like folks I could talk to. So let's see. Let's go back to EZNEC and go back up here, and here's a 160 loop. Here is that loop in free space. There's the loop. Feed point for the loop is, is 0.5. North is in Y, this is east. This isn't up very high. I mean, it's not even up very high for 40 meters. It's only up like 15 feet to 25 feet. So didn't expect that it would do much. Figured it'd burn a hole in the sky. And that's what I should see. But first, let me show you what the pattern for the antenna would be if there was no ground. And this is going to be the run. Boom, 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 boom. It was calling neck. And this is kind of what it looks like. So this is kind of something round with some dimples in it. And I'm going to do an azimuth slice. I'm going to cut it at the equator essentially, and that's the pattern that you would see if there was no ground. And there's some directivity to that. This is east. That's north. It was cool. And you see, at least from my point of view, the fun of looking at some of these patterns and being able to rotate this, look at different cuts. So let's see, you can also do an elevation cut. Let's see what we have there. I guess that isn't going to be so relevant right now. So I'm going to go back here. So there's a run. And open up a different file, and here's with the real ground. Now, the real ground has an electrical conductivity and it's got a dielectric constant. Both things electromagnetically dork with the field, the far field. You sort of expect when you put this in that the radiation's going to go up and not so much to the sides. So if we open that, again, there's the same antenna, do a run, and wow, look at that. I mean, there's about hardly no directivity to that at all. And if I do an azimuth, again, and I'm going to do it at sort of an intermediate elevation angle, and I show that plot, it's almost circular. There's a little bit of directivity left, but not much.
This is with your ground?
This is with a real ground.
How did you do that?
I changed that parameter in the code, and one of the things you can enter here is a ground description. So, and I used parameters that they had. I didn't measure the ground conductivity myself. They use 0.05 1/ohm meters for the electrical conductivity. They use a dielectric constant.
But where did you put your ground? Where's your ground point at?
It's not a single point. This is a plane underneath the antenna simulating the Earth, simulating a flat Earth.
So you laid wiring down?
I did not. So I put the antenna up. I made no ground plane intentionally. I'm using the Earth that's there.
Okay.
And the difference, you can see the difference between having the real Earth there and absorbing the radiation compared to what I had when I showed you the pattern that had no ground at all.
So the no ground at all would just be in free space then?
Would just have been in free space.
Mhm.
Yeah.
So can you adjust the height above ground of your loop?
Sure can, absolutely.
Because I don't see a parameter for that on your
Well,
screen there.
that's implicitly in the wires here.
Oh, okay.
Z's the height.
All right.
So you can see now, actually I went
So you
around.
have the actual heights?
Yeah,
in there.
so I
Okay.
went around to the tree and I went 18 feet, 15 feet. I mean, I didn't do it very carefully. One of the things I found was, especially with this loop, it doesn't make much difference. I mean, it's so much of a sky burner that even if I went and changed all the heights by 5 feet, even 10 feet, compared to a wavelength, that's a pretty small change. For this antenna, that wouldn't make a big difference. If I'm on 15 meters or 10 meters, and I change by 5 feet, it'd make a big difference.
So this is basically NVIS.
Yeah. Might almost be just buried a wire in the ground.
Yeah, exactly.
Just almost. That's right. That's right, Joe. So So I guess here's a case where the elevation slice has some bearing. And you can see the scale here is dBs. So like you would expect, I'm burning a hole in the sky.
Yeah, it's only 5 dB down at 45 degrees.
That's true.
You'd probably like that lobe to be quite a bit lower, though.
Yeah. Yeah, that's right. I used this antenna in 2011 in the ARL DX contest that's coming up in December. And I had, I don't know if you know this contest, but 160 is only good at night, right? So if you're in, and this contest goes 48 hours, so it's 2 nights. It's Friday night and Saturday night. So if your wife has something scheduled for you on Saturday, you're really careful. By Sunday morning, you're dead beat. And I operated, about 8 to 10 hours each night, from 6 at night to, midnight or 1. And with this antenna, I had 325 QSOs. Well, it's not too bad.
What are you running for power, just barefoot or you put?
No, I had an amp for this. I was running 300 watts.
CW.
CW, yep. This is a CW contest. The CQ has a sideband part. There's 2 of them in February. This one is just CW.
You notice any difference between high and low soil moisture?
Not with this one, but I had a vertical for 80 meters, and it wasn't working for squat, and we had a snowstorm, and I could work Europe gangbusters. Yeah, that really made a big difference.
Drought and spring rains.
Yeah.
Well, the snow cover did change.
Yeah, the snow cover did for the vertical. This one, we're so low. I mean, I could do a run here with an ideal ground plane, with a full copper plane to see what it looked like. But there's a little bit more of a story here. So I got no directivity, and I'm burning a hole in the sky. And I was pretty sure I could get more QSOs in this contest. And if you come back to this park, let's see if I can. This park out here is where the Bellevue Amateur Radio Club has its field day. And every year, Kevin Ferris climbs that tower, climbs the water tower. So, let's see, I forgot to show you a couple of things here. Let's see if I can get it. This is a picture of our house. This is looking to the west. This is our home from the street access. This is a view to the west, a break in the trees. The pine trees are over here on the left. You can hardly see it, but back up in here, I don't know if you can see, there's a water tower back there. So here was the answer to my prayer for a 160-meter antenna, that water tower. I got Kevin to climb the tower, and I strung a 1,000 foot of wire. That's like 170, 180 bucks worth of THHN from Menards. And I strung it. I fed it a quarter wave in from the end, so it's this much is a dipole, which I use now. Actually, I use it on 80, and it's a 160 meter dipole fed in the center with a 250 feet of 450 ohm line. Obviously, not everybody can do this. And I strung this through the trees. Kevin climbed the tower, and I went through all kinds of contortions to get over a bunch of trees here and terminated it out there. So I had a 2 wavelength long wire and sort of end-fed. Not end-fed totally, but in. I fed it in a quarter because the impedance would be pretty easy, pretty close, I hoped, to what it would normally be. The tuner that I would use probably shouldn't have been too dramatically different. And it wasn't. So we go back here, and let's see, close this guy. And open this, go back up here. And let's see, here is a free space. Let's start with the free space guy. Here's the model. I can't expand this too much, I don't think. This is the model. I went out and met, again, I eyed all the trees. I'll show you a hand picture of this in a sec. Point 4 is where the feed was, and this is 1,000 foot of wire. Let's see. See if I can bring this up here. Here's a cartoon. Here's a cartoon. This is a cool cartoon. Here's a house. I've got a 4-section steel telescoping mast. That's the feed point. That was the 0.5. Here's all the pine trees, wire strung through there. There's a sycamore, big old sycamore tree that, just on the edge of the park. Then I came down. It was kind of hard to keep it up very high. Kevin climbed the tower, gave me a connection off the end. I didn't do my measurement very well, and after I got this all strung out there, I had another 30 feet beyond the tower to go. And I wasn't going to horse with the 970 feet of wire that went the other way, so I had to go past the tower a little bit. In fact, there was a tree out here. And this is kind of the model for it. And so what does this look like? What does this look like? So here's the antenna, and this is no ground. Is this cool? This is really cool. This is like a horn out here, okay? Now, so there's no ground here of any sort. 3-dimensional pattern, like it was, one wavelength running at 1.8 megahertz, just 1.825 or something. And so there's a horn out here, there's a horn here. Actually, this is a little bit bigger than that guy. And when you feed the antenna at one end, it's not quite symmetric. I don't understand the electromagnetics for that, but I've seen that a lot. And there's a couple of lobes in this case that look like plates, like dinner plates that are at a little bit of an angle. So let's see. Let's do an azimuth cut. Boom. Here's what you got. So if I look down on the top of this antenna, I should have a lobe out here. Okay. This is the what looks like a horn out. Here's the 2 dinner plates, and I've one in the back. You can see this guy's a little bit stronger than the lobes here. I'm feeding it at this end. So, last time I had an antenna, I put real ground in, all the fun stuff went away and I burned a hole in the sky. So, we can see what real ground does.
You've got a good lobe going towards Europe there. And then
Yeah,
going to the
yeah.
northeast.
Oh, I didn't get to Europe much.
No, yeah.
The guys that get to Europe from here, Joe, who is it? DI that operates from Reynolds' place?
Yeah, but a lot of times Bill Holmeston, K0HA is the one that does it.
He does it too, yeah. And I
He's
can't-
out near Seward.
Yeah, he has a great setup there, that's true.
Yeah, he's even got beverages to listen.
Yeah. Well, I told you about Spangler's Field. I did a beverage out in Spangler's Field north of this one night. And that worked fine until that worked great Friday night of the contest. And then it snowed on Saturday. And snow takes away what the beverage is supposed to do. You need bad ground, right, for the beverage to work right. And it didn't work right. Okay, let's see. We're opening the real ground. And we're going to do a run with real ground. And lo and behold, there's the pattern for real ground. Directivity didn't go away in this case. Directivity stayed the same. And if I do an azimuth slice, Now, at ground level, at zero up from the horizon, I don't get anything in this case because I got earth there. So this cut is going to be up at 35 degrees. And we'll do an elevation cut in a sec. This just shows the azimuth pattern, and I got lobes. So cool for me, because in this contest, there's a lot of folks on the East Coast, and there's some out in the West Coast. And in fact, I used it the next year, 2012. I had, with the same number of hours operating, so that's like 20 hours out of the 2 days, plus or minus an hour, conditions not terribly different. The operator, it was just as stupid in 2012 as he was in 2011. I had 525 QSOs compared to 325. Made a big difference in QSOs. And part of the reason for that is not only do I have a lobe east and west, let's see what I want to do, I beg your pardon. I want to do an elevation slice now. And we're at 180 degrees, and there's the elevation. And if you remember, I can't remember where the comment came about wanting to have something lower from burning a hole in the sky. You can see that I'm getting a fair bit of radiation, even, that's 35, even down at 20 and 30, which is pretty hard to do without getting something up pretty high at 160 meters. So this was fun. You know, for an amateur, I'm not like HA, and there was a guy out in Broken Bow too. Steve Lloyd drove me past his place, and he's in Maine now. I mean, there's a couple of fellows that, you know, spend $20,000, $30,000 putting up stuff. This was $160 of copper wire. In any event, so that's kind of my story. This was fun to do. The modeling here didn't change very much, but showed me how it operated. On the air, one of the things that I was able to do is when I was first testing this out, I had the loop going at the same time that I had the long wire, and I was talking to somebody in Indiana or Ohio, and there was somebody in Wisconsin. And very clearly to Ohio and Indiana, my signal on the long wire was a lot better than the loop. Wisconsin was listening. A guy in Wisconsin, he broke in, said they're about the same for him. And Wisconsin was probably not far off this minimum here. And then the loop, even though it might have been a little bit weaker, still gave comparable signal to the Wisconsin person.
Your null got out that far?
Beg your pardon?
You say the null got out that far?
No, I'm saying that there wasn't much signal to Wisconsin.
Yeah, that's
with
what I'm
the wire.
saying.
Yeah.
That's a null there. It's-
Yep. Now, do I believe that the real signal, if I could go out there and measure, 5 wavelengths out and make a really careful E&M measurement of the fields and waves, would be the same number of dB as we have here? Of course not. This is not that accurate. But there's certainly a null there. Without a doubt, there's a null there. Okay. Let's see. So I guess bottom line is some of the things that you can do with this. I've got a number of antennas that have some sort of arbitrary length dipoles. I feed them a 450 ohm line. One of the nice things here is you can run a model on that antenna at different frequencies, not the half wave. I mean, it might be some unusual length, and you can run and see what that pattern is. I was trying to get there was a TY1, I can't remember, about 3 or 4 months ago. I was trying to get a DX station, and so I put up, and I didn't have an antenna up for 20 meters at the time, so I did a 20-meter antenna, but he was on 17 and 10 and whatever, and so I just fed that with 450 ohm line and tuned it, and I did a model of that, which helped me understand what the pattern was. You can do that sort of thing. You can see effects from ground. If you can see, we've talked a little bit about height. you can see the height effect on the radiation at some elevation angle. So you can get a sense, if I went and took my antenna, suppose I have my antennas up 33 feet and I'm on 40 meters. If I put that up another 5 feet, does it make a difference? Almost certainly not. We could run that. If I get up 10 feet, does it make a difference? This code could give you those kinds of differences. So if you're interested, if you do have wire antennas, it can tell you that sort of thing. Let's see. This is an email for me. You're welcome to send an email. I hope someone would try EZNEC. You can do that with a free version download. It doesn't cost $1.
Is this the one you said was $130?
Yeah, there's two versions. There's a basic and a basic plus. The basic is $89, downloaded off the internet. And the basic plus is $139, I think it is, and you download that too. Because I do a lot of this and I'm interested in it, spending $130 is reasonable. For most folks, it might not be. I can understand that. You could try the other code, which is shareware. It's based on MiniNEC. I don't know the graphics for it, but so. That's my talk. Hope someone will try it. And if you have an antenna that you would like to just do a parameter study on, I can do that for you. Get the dimensions for you. The hardest part about this is measuring your antenna and doing the geometry or trigonometry that goes with figuring out the X, Y, and Z coordinates of the endpoints of your wires.
Did you model your loop on any other frequencies, like say 20 meters to see what it would do, or 10?
I didn't on 20. On the loop I studied a lot. I have a little AUTEC analyzer. So I took the 450 ohm line off the drive point, climbed the pine tree, and held that with Steve Lloyd, AG0L at the bottom, recording numbers that I shouted out to him. And I measured the resonant frequency on 160, on 180, and 40 meters. And like I was telling you, Mitch, it was unreal close on 160. It was like 1% or 2% for the resonant frequency. So one of the things you can do in this code is you can set it up and it will run the code at a number of frequencies through your range, and you can then, and it'll display that, and you can click on a point on that curve and you can see what the reactance and resistance is at different points. So I take resonance to be where the reactance is 0, and it was within 1% or 2%. Which is, I just couldn't believe that. And on 80 meters, it's the same thing. It was pretty close. And now, and the overall impedance wasn't as close, 10 or 15%. But I thought that was surprisingly close, given that, how did I figure out the heights of all these things? That looks like 18 feet. So it can't be very sensitive.
So say on 40 meters or 20 meters, your radiation pattern would look a lot different too then, wouldn't it, than on 160?
Yeah, but even at 40 meters, I'm not up 1/4 of a wavelength yet.
Oh, okay. Right.
So if